everybody. It's our 7th video lecture, I think, or class for analysis. And I want to remind everybody we have homework due next time. And today I want to open up the floor to any questions you might have about the homework or any questions you might have about anything we've covered. And you can ask anything you want. So anything on your mind that you'd like to ask about?
There are other rules for proofs, like and, or, stuff like that, not like the symbol for not. Are we allowed using those out, or
You can
should we
use-
stick with this one?
You can use different symbolism than what's in the book if you're accustomed to something. Make sure the first time you use it, just that it's clear to me what it is by writing it down. This means not.
Okay.
So for one thing, Audra, the way that I was taught, not was written like this. That was the not. I don't know if that's the not that you have in mind.
What are we learning?
Like a little, like that.
Like a corner?
You were like this.
Yes.
Okay. This is what I'm used to seeing as not.
Okay.
So you know, just as long as you define, let me know this one time. This symbol means this, and from that on, I'm okay. I know that that symbol for you means a particular thing. So if you want to use something else, it's okay in terms of symbolism. What else would anybody like to ask about? Any of the homework problems that you say, I don't know what to start with here, or
I do have a question.
yes, sir.
For number 2.
Yes, sir.
C, or parts C and D.
Okay.
I did those proofs, and the way I did it was to find a common denominator. And I don't know that that's an okay thing to do.
For parts C and D,
Yes, sir.
it's kind of tough for me to understand what is meant by that. Okay?
Well, I get to a point in the proof where I have to add 2 fractions that do not have the same denominator.
Okay.
And what my question is that something we've established? Is that that's something we can do?
It's not something we've really established, but it'd be okay. We'll let that go. Okay?
Okay.
And we'll say we know that we need to get common denominators. All right. That'd be okay. You know, I haven't looked at 2C in a long time, or 2D. I hadn't looked at these problems since the last time that I assigned them. But one thing that I wanted to tell you in terms of the problems are once you do one problem, part of a problem, then that is a fact. Once you've proven it, that's a fact. And you can use that to maybe do other problems. Okay? And that, I've looked at one with people in terms of your classmates, some people in here have asked about problem 1. And once you establish part A of problem 1, you can use that to do some other parts of part 1. Okay? Is that okay with everybody? Anybody have a particular problem they'd like for me to look at? We're okay? Well, don't forget, the homework is due on Friday, I should say. And once you turn them in over the weekend, I hope to have them graded and then give you another chance to revise them. Okay? So that's what's to be expected. Please work on them diligently now, because it makes you more prepared for any type of revisions that are needed, or be more, you're in position to be more effective positively by comments that I make. Okay, so do all the work that you can now. Well, if there are no questions, then what I'll do is I'll move forward. We were talking about last time about bounds for sets, and whether a set was bounded above or bounded below, bounded set, unbounded set, upper and lower bounds. And so now I want to extend that by writing the following definition on the board. And so we're going to start off with letting S, script S I'll call it, be a non-empty subset of R. Okay. The number U is said to be or I'll say the supremum of script S denoted by U equal to soup of script S. If these two are satisfied, the following two things I'm about to write down are satisfied. And first, U is an upper bound. Of S. And two, so the second one is, if V is an upper bound of script S, then U is less than or equal to V. Okay, give everybody a second to write that down. So that's what it means for U to be the supreme. What does it mean for U to be the supreme? It's an upper bound, U's an upper bound, and if you give me any other upper bound, U is less than or equal to. This supremum is also known as the least upper bound. So, if U, the soup of script S, is also called the least upper bound. Of script S, a least upper bound. Sometimes we abbreviate that LUB. So it's an upper bound and it's the smallest of the upper bounds. Well, if we have a supremum, we can have something analogous to it with the involving, instead of the upper bounds, the lower bounds, and that's called an infimum. So let me write it down, its definition. So again, we're going to let S be a non-empty subset of R. Okay. The number, I'm going to say L, script L, is said to be the infimum of script S, and that's denoted by L equal to the INF of script S, M script S. If these two things happen, the first thing is L is a lower bound, script S, and I didn't write down the word and, but it is and if, I'll say W is a lower bound of script S, then the relationship is that W is less than or equal to L. Okay, so that's its definition for an infimum. Again, we can have a different name for the infimum. Let me write that on the board. So, an infimum, script S, is also called the greatest lower bound of S. And we abbreviate greatest lower bound by GLB. So it's the lower bound, but it's the biggest of the lower. I'd like to look at some examples. Let's give everybody a second. If I look at minus infinity up to 2, and somebody said, okay, that's your set S. And then the first part was, what's the supremum of S? Okay, before we answer, let's make sure we understand what's being asked of us. We're looking to see if there is a number out there that is a lower bound, that is an upper bound. Okay, it's got to be an upper bound. And it's the smallest of all the upper bounds. Okay. So is there a number for this script S that's an upper bound and it's the smallest thing of all the upper bounds? The answer is yes. What is that? 2. 2 is an upper bound. And if you give me any other upper bound, 2 is less than it. Less than or equal to it. B, somebody says, what about the infimum of script S? Well, what would you be looking for? You'd be looking for a number such that it is a lower bound of S, and it's the greatest of all the lower bounds. Well, first of all, S is not bounded below. There is no lower bound. And so here, the infimum of S, this does not exist in this particular example. Let's look at another example.
I'm sorry, in that example,
Yes.
is that negative infinity to 2 or Z?
It's minus infinity to 2.
2.
To 2, yes. Thank you very much. I'm sorry. Okay, it's another example. What if I have open interval on the left from -7 to closed interval on the right of 5? And let's let that be S. So here's the first question that I have. What is the soup of script S? So we're looking for an upper bound for it. That's the least upper bound, the smallest upper bounds. John, you have an answer, I think.
I believe it's 5.
5 is correct. 5 is bigger than or equal to everything in the set. And if you give me any other number that's bigger than or equal to everything in the set, 5 is going to be less than or equal to that number you gave me. And what about an infimum? Chuck, can you give me an infimum of this?
-7.
That's right. Is small, -7 is less than or equal to everything in the set? And if you give me any other lower bound, -7 is bigger than or equal to it. I'm going to change the problem. I'm going to put it with a closed bracket here. I want him to do that. I made a mistake. It doesn't change my answers here. They're still the same. But I want to make that closed bracket. That means that -7 is not in S, but 5 is. So one thing I want to tell you, the soup, if it exists, can be in the set or maybe not. And the same thing for the M. Okay? Doesn't have to be in the set, but it could be. As another example, what if we looked at the set of natural numbers? What was the set of natural numbers? Yeah, so it's 1, 2, 3, 4, and look, I'm just going to look at this. I'm going to tell you, as an example, but we're really going to prove this, that the soup of script N, so is there some number out there that's bigger than everything in the set of natural numbers? And if so, is there one that's the smallest one of such numbers? Well, what's the answer? Does the soup of N exist or not? No, this does not exist. And we're going to prove that. And the second thing, or B, is the M of n, does that exist? Is there a number out there that is less than or equal to everything in n, and out of all the numbers that are lower bounds for script n, that number is the biggest one? Yeah, there is one. Can you tell me what it is? Chuck, you know what it is? One. And again, that's in the set. Okay, but it doesn't have to be. It is in the set. Okay, so that gives us kind of an idea of supremums and infimums. They don't have to exist. Okay. But they can. Next thing I think I want to do is I want to prove a fact having to do with supremums, and you can prove an analogous fact having to do with infimums. Let me look at the fact having to do with supremums. It's straight out of our text. Here's what it says. It's a lemma. It says a number u is the supremum of a non-empty subset script S of R if and only if U satisfies the following conditions. There's two things you got to satisfy. One is S is less than U, and that's true for all S in script S. And two, if V is less than U, then there exists a T or S prime element of script S such that V is less than script X, or S prime, I should say. Those are two things. Okay, we won't prove this. I'm just going to give everybody a second. You know, I want to take a second. We're going through material in this class. I want to take a second to tell you what the heck are we saying here? What we're saying is the following. The definition for U being the supremum, that definition is the same thing, whatever U satisfies to be the supremum in the definition, is the same thing as U satisfying these two qualities. Okay? So the definition of supremum's two qualities it has is the same thing as these two qualities. Is that okay? That's what's being said. A lot of times I think it's easy to get caught up. We're proving things. We're going through without really realizing what it is that we're proving. Okay? All right. So I'm going to give an example. Okay? I'm going to back up just for a second. But we're going to get to this, and I'm going to prove this just a second. I'm going to come over here to the side just to remind me of something. You know, in the homework, I was working with somebody for the homework, so I'm going to revert back to it for a second. 1A from the homework, it says the following. It says, if A plus B equals to 0, then B equals to minus A. You can write this down or not. You don't have to write this down. I want to explain something. It's not, you say, well, this is a bunch of symbols. What is it it's saying to us? Okay? This is saying, this is a way of reading it. If you have first plus second equal to 0, then the second had to be equal to the additive inverse of the first. First plus second equals 0 means second equals to minus first. Did you guys hear me? That's what that means. And so I'm going to do a problem from your homework for you right now. Maybe you do want to write it down. And then I want to use that to do part B. So let's say this is done. Say we prove this. Then for part B, 1 over B, only 1, it says prove that minus a minus A equals to A. So I'm going to prove this. So here's the way I'm going to prove it. What I'm going to do is I'm going to use part 1A to prove 1B. And the way I'm going to do it is the following. I'm going to say, note, one thing I know is that A plus minus A equals to 0. So give me a second. I can write that down. How do I know that? Because A is a number, and minus A exists as a number. And what does the property that minus A has, according to the algebraic properties of R, the properties that it has is that if you add it to A, you get 0. That's what property it has. That's the only definition of minus A. Now look, if I try to apply part A to this, what it would say is the second. This would say minus A, the second, is equal to minus the first. Is that all right? So I write down minus A is equal to minus A. Well, duh. Minus A is equal to minus A. That isn't too helpful in proving this. Okay? So instead, I'm doing this one problem for you. Oh, let's get the squeaky jar. Oh, let's squeak it. Instead, what we could do is, we could rewrite this, is that minus A plus A equals to 0. Because A plus minus A is the same thing as minus A plus A. Is that okay? Now applying 1B, applying 1A, I should say, that we're claiming we've proven. You guys got to prove it. We have, what do we have? So again, this is stressing, do we know what the statement is? We have what? We have the second. What's my second here? Go ahead, Nathan. What's my second? A, the second guy involved in this addition, is equal to minus the first. What's the first? Isn't that what I'm trying to prove? Minus a minus A equals A. There it is. I'm done. Is that okay? That's a way of doing 1B. Okay? And the reason I'm pointing this out is just to say, let's remember what these symbols mean. Okay? That's what we're looking for. What is it that we're stating with these shorthand notations? So getting back to our problem over here, our lemma that we're going to prove, what we're saying is, I'm going to get out of the way, but what we're saying over here is that if you give the definition for what it means to be the supremum of a set, those two conditions are the equivalent to these two conditions. Okay? That's what's being said. Okay. All right, so we're going to prove it. Sorry about that kind of interruption in our proof, but I just think it's good for us to remember what is it we're doing. Okay, so here's the proof. Well, the statement is an if and only if statement. So that means we're going to have two proofs, really. Now, the first proof, we said going forward. What does forward mean? Well, that means in this case, we're going to let u be equal to the supremum of script s. Okay? What is it we want to show? We want to show two things. One, s is less than or equal to u for all s elements of script s, and part two, if b is less than u, then there exists an element s prime of script s with v being less than s prime. Okay? That's the two things we want to show in this direction. Okay, well, one is easy. So here's what I mean that it's easy. Since u equals to the supremum of script s, by definition, what does it mean for u to be the supremum? It meant two things. What was the first thing? It was that u was an upper bound. upper bound. By definition, U is an upper bound. Of script S. Okay, so that's a word, upper bound, or phrase. What does it mean to be an upper bound for a set?
Greater than or equal to all the elements in it.
That's right. It's greater than or equal to all the elements in script S. So that means, so for all S in script S, S is less than or equal to U. That was one of the things we wanted to show. So I'm done with part of what I need to show. That's good. Now I need to work on that second thing. Okay, we will show two in the following way. So here, I'm thinking about trying this way. And look, we're trying to prove something. It doesn't mean that you get it right immediately every time. You try something. Okay? Because here's what I'm going to do. I'm going to do it by proving the contrapositive. So here's what I'm going to prove. What I'm going to prove is, suppose the opposite of the conclusion. Suppose the opposite of the conclusion is there exists an S in script S with V being less than or equal to that particular S. We're calling it S prime. So suppose for all S element of script S, the opposite would be that S is less than or equal to V. And that would be the opposite. We need to show the opposite of our hypothesis for 2. That is, we need to show that U is less than or equal to V. Okay, well, since for every S element of script S, S is less than or equal to V, what can you tell me about V? If that's true, what can you tell me about D? Give yourself a second. Hey, if V is bigger than everything in S,
It's an upper bound.
then V is an upper bound. Remember, we're assuming that U is the supremum. So what does it mean to be the supremum? It means this. For U to be the supremum, if you give me any upper bound, U is, how does it compare? How does the supremum compare to any other less than or equal to? It's less than or equal to. It's the least upper bound, the smallest. So that means U has to be less than or equal to V. And that's what we wanted to show. So that's the contrapositive statement to part 2. And so when you prove the contrapositive, you've proven the original statement. Okay? Is that okay with everybody? That's the forward direction. If you don't mind, I will also prove this a different way. Prove part 2 by contradiction. So here, look, I'm going to put this in parentheses because this isn't necessary. Okay? But how do we prove it by contradiction? We suppose the if part. So suppose V is less than U. And the opposite of what we wanted to show. So then, suppose the opposite of there exists some S such that V, some S prime in script S, such that V is going to be less than that. The opposite of there exists one. Suppose for all S element in script S, S is less than or equal to V. So it's essentially going to be the exact same argument.
So you basically trying to say here that V is not an upper bound?
Here, yes. Well, I don't know about that for the contradiction, but V isn't going to be an upper bound. Okay? That's what the statement in the lemma is. Okay? The V isn't an upper bound. Okay. Okay, so here, suppose this is happening. Then, that would say, we're going to contradict this. Then that would say that, again, the same argument, that V is an upper bound. Okay. Since U equals to the sup script S, then U would have to be less than or equal to V, and that contradicts the assumption that we're having. Okay? That V is less than U. So same argument, essentially. Just a different framing of the statement. Anyway, we've got the forward direction. Let's go in the opposite direction. So what's the opposite direction? We're assuming that the two characteristics of U are satisfied, the latter two things, for this lemma. So here we're going to suppose U satisfies the following. The first thing is that U is an upper bound I'm sorry, wait a second. Let me make sure that I refer back to the problem correctly. 1 second. It's not that. We assume that for all S, I made a mistake, for all S in script S, S is less than or equal to U. That's what we assume. And, 2, if V is less than U, then there exists an S prime, element of script S, such that V is less than S prime. We want to show U equal to the supremum script S. Okay, how do I show something's the supremum of script S? The only thing I got is the definitions of the supremum. To be the supremum, you've got to satisfy two things. One, you're an upper bound, and that you're the least upper bound. Is that right? Okay, so here, to show that it's upper bound, since for all S, element of script S, S is less than or equal to U, then that means, by that assumption that we're assuming 1, then what does that tell me? U is, if U is bigger than everything in S, then U is, that's right. Of script S. And that's the first thing that needs to be satisfied for you to be the supremum. That was in the definition of the supremum. That's the first thing. What was the second thing in the definition of the supremum?
It's the least upper bound.
Right, meaning if you give me another upper bound,
It's gonna be bigger than you.
that's right. Okay. Now, let, let's say W be an upper bound of script S. We must show U is less than or equal to W. That's what we got to show. Well, in order to prove that, let's do it by contradiction. Let's suppose not. We will suppose that, okay, we're trying to show that U is less than or equal to W, but let's suppose that W is less than U in attempts to get a contradiction. Well, W is some number that's less than U. What are we assuming? We're assuming over here that if you give me some number less than U, then there's some number in the set. Okay, there's some number in the set, that is bigger than the number that's less than U. So here, I'm giving you W. That's playing the role of V over there in my assumption. So by assumption, there exists an S prime, element of script S, such that W is less than S prime. Well, what does that mean about W? I'll tell you one thing, it's not. I'll tell you one thing W isn't. It's not an upper bound, because there's something in S bigger than W. So W isn't an upper bound. But it is an upper bound. That's the contradiction, because it is an upper bound. Okay? Thus, we made an assumption that was incorrect. What we assumed was that W was less than U. Thus, that means that U has to be less than or equal to W. So that tells us that U is equal to the supremum of S. And that's the proof. Yes, sir.
After solo assumption.
Okay.
Less
Right. So the assumption that I'm referring to, Dalvin, is this number 2 that we're assuming for this part of the proof. What does this number 2 say? It says, hey, look, you give me something less than you, then there's some element in S that's bigger than the number that's less than you. And so by that assumption, there exists some number in S, okay, that's bigger than the guy that's less than you. That's what I'm referring to. Is that okay with everybody? Anybody else with a question or comment?
Is there a shorthand for upper bound? Or is it just you have to spell it out?
We just normally, not that I'm aware of, I always spell it out, up or down. Sometimes people might put U period B, but I mean, that's okay, but I just spell it out.
They're open, but brackets or
There might be some kind of bracket notation that you can use, or top, plus or minus, for upper or lower bound, but I'm going to write it out. I want to emphasize one more thing before I move on. If you give me a supremum, what this limit says, if you give me a supremum, if you give me something just smaller than it wouldn't an upper bound. Is that okay? That's what this limit is saying, one of the consequences of this limit. You give me something smaller than the supremum, it wouldn't upper bound. Is that okay? That's what it's saying. Here's the supremum. You go back just a little bit. Hey, there's something from the set in between those two numbers. That's what's being said. That's good. Well, we could say a very similar statement. Instead of it applying to upper bounds, it would apply to lower bounds. That's right. So I'm going to say something very similar. And it's written in the book. So here's a lemma. Okay, so here's what the lemma would say. It says, given a non-empty subset, script S, the number, let's say L, is the infimum of script S, if and only if L satisfies okay, so analogously to the previous one we had. Okay. Look, to be the infimum, you've got to be a lower bound. The analogous number one is that L is going to be less than or equal to S for all S elements script S. The analogous statement for the previous lemma, for number two, is if you give me some number, if, let's say we give V, so if L is, I think it's less than V, okay, then there exists an S prime element of script S such that S prime is less than V. I'm not going to prove this. It's got an analogous proof, Chuck. Melissa's got an analogous proof, similar to what we did. But here's what I want to think about. Look, this lemma is saying, hey, if L is the infimum, the two properties for being an infimum match these two guys. Okay? Let's think about this for a second. Here's what I'm thinking. If you're the infimum, you're lower bound. Okay? To be a lower bound, you've got to be smaller than or equal to everything in the set. That's what one is. Okay? Now, if you're the infimum, that means you're the greatest lower bound. You're the biggest thing that's a lower bound. So if you give me something bigger than it, it can't be a lower bound. That's what this is saying. So if you give me something bigger than it, there's something in S that's smaller than what you gave me that was bigger. Meaning V can't be a lower bound. Is that all right? Because it's not smaller than everything in the set. That's what it means. And its proof's analogous to what I did for the other one. Is that okay with everybody? Okay, so I'm not going to prove this. So what I'll say is just to state the proof is analogous to the proof of the other one. Of the previous one. Maybe I ask you to do it for homework. Maybe. Very simple. Well, instead we're going to move on. And I'm going to state something that's called the completeness property of R. Okay? That's what we're going to do next. Yes, sir.
Is there a kind of shorthand for writing in field, or saying something's in the field, like how we said U is equal to super?
Yes. So the infimum is this. That's the infimum. Okay. here's the completeness property. This is a fact, something I want you to be aware of. We're going to take this as an axiom. That means it's something we're stating as fact. We say this is just true. Okay? Not something we prove. It's something we just say this is what we're taking for granted. And here's what we're thinking. It says every non-empty subset of R that is bounded above has a supremum. So if you've got an upper bound, and you're non-empty, you've got an upper bound, there's a supremum for that set that exists. We're not saying the supremum is in the set, it's just that the supremum exists for that set. That's what we're saying. I will just say a comment, say this. From the completion property, of R, one can prove that if S, there's a subset of R, that if you give me some subset of R that is non-empty, and bounded below, then thema of S exists. So the completeness property is an analogous statement about infimums existing for sets bounded below can be derived from the completeness property. Okay, so I want to say that. We got 2 minutes. I want to give you a named fact. Okay, here it comes. This is called the Archimedean property, and here's what it says. It says it this way. It says, if X is an element of R, then there exists an n sub X element of the natural numbers such that X is less than or equal to, so I'll say less than n sub X, that's what I write. But I'm going to write some words with it, just a second. It says less than or equal to. It doesn't matter if it's less than or less than. I'm going to write down less than or equal to magic. That's what it says, Archimedes. Okay, these are a bunch of words, Brad. Mary, it's a bunch of words. What are they telling us? Okay, Megan, here's what it says. You give me a real number, there's a natural number bigger than it, essentially. Okay? What that means is, another way of saying this is the set of natural numbers is not bounded above. That's what this means. And I said to you earlier, as an example, the seven natural numbers in bound above, that's the Archimedean property, and we're going to prove that. And I think we've done enough for today, so we'll save that for next time. Okay, don't forget your homework is due next time, so please turn that in, and I'll grade them over the weekend and give you a chance for rewrites. And if you have any questions, don't hesitate about coming by. Today, my office hours are going to be cut short. There's a meeting that I need to attend, so I'm going straight to that meeting instead of going towards my office. Sorry. What was the homework again? The homework was the phone. So I'll write it over here. Don't forget, this was the homework. So from pages of our text, so on pages 30 and 31, do numbers 1, 2, 4, 5, and 20. Thank you very much.